Good morning, everyone. Say it back. I got a new, nicer webcam. Made an investment. I bought a nice little fancy. We're streaming in 4K now. We're streaming in 4K. I got a nicer webcam, um, so you can see my ugly mug in 4K. Really, it's so that you can see your TAs lounging on my unmade bed in better detail. So that one's Milo. He's relaxing, and you'll just have a little bit better view of him today. Well, and for the foreseeable future, I suppose. Um, I guess I'll use this opportunity to one apologize for the Canvas announcement. I'm not a perfect person. Sorry to those of you that I freaked out. Um, what was the second thing? Oh, and number two, your Unit 2 homework is posted. Okay, I guess I have more things to apologize for. I said that I was going to have your Unit 1 homeworks back by today. That was a big fat lie. I've only graded 43 of them, and I spent all weekend doing it. So I'm not proud. It just means that I'm taking more attention on each of your assignments, which should be a good thing. Like, you're getting the grade you're getting regardless. I think that you would benefit in learning scientific writing the more feedback I can give you. So, those some of you are getting some nice feedback, which is a bigger priority to me than like giving you a grade. I think that helps your learning along. So, um, please, I guess the lesson is in exchange for you giving me a few more days to do this, really look at those comments when you get them back. Hopefully, you'll learn something from them. Um, yeah, and expect those on Friday at the latest. I'll make a good plug tomorrow, and then Friday all day. In my defense, 80 students is a lot. And I don't see half of you all the time, so I greatly underestimate how long it's going to take to grade all your stuff, especially written assignments. But I want to give each of you your due diligence in your grading. So I'll have that in mind going forward, especially with your second writing assignment, which is your final. So sorry. Um, I did hold up the other ends of the bargain, which is the part where I just assign you more stuff. Unit 2 homework is posted. You'll also see it's only 7 problems, but yeah, it's 7 problems like A through G on some of them. Um, it's really not as bad as it seems. I also just all this whole time I've forecasted that the math is coming. Oh, the math is coming. The math is here. The math has arrived. Um, and the entirety of Unit 2, for those of you enrolled in person or with free time on Thursday mornings, is dedicated to doing that homework together. 7 problems we're spending 3 whole weeks on. Because it will be graded for correctness. Correctness doesn't matter in EPI. So we'll work through it together. I want to reward the motions of studying. And this is the best way to study for your exam. Like, your exam questions down the road are going to look pretty much exactly like this homework, just with different numbers and situations, right? Okay. Um, so in that assignment posting, you'll see like the thing itself. It is a Word doc. You can type in it and like space the questions out. That's fine. You can also put it on your iPad and write all over it. I've given you enough space to do that. You can also print it out if you're really wildin'. You can print it out. If you're going to do that, the submission will only allow you to submit a PDF. If you really want to hand it to me in person, email me and we could talk about it. If you really want to print it out to me and hand it into me in person, we can make something work. But yeah, it's gonna have to come back to me as a PDF at some point. Yeah, and you'll also see the schedule. This week in activity, we're doing questions 1, 2, and 3. I think next week. Nope, next week is spring break. The week after spring break, we're doing 4 and 5, and the last week is just 6 and 7. That's like an hour per problem. So really, these are meant to be collaborative, and it says that in the instructions. So activity time is like, I'll set it up, you'll try it yourselves, and then we'll do it together. And we will make it through, and you will get the right answer. So That's how Unit 2 homework is going to look. I know it's a problem set, not a writing assignment, and it looks very different than the last one. But we're switching gears. We're switching gears, and now we're epidemiologists with a capital E, okay? Quiz 6 is posted. Again, it covers what I'm about to say, and last week's lecture as well. So have both up if you're going to be control Fing and trying to find bits and pieces, okay? It takes both. And there's some math. Not as much as the unit homework. I think you'll have to divide a number maximum 3 times. But there is math, and so I'll just tell you that before you open it. Last week, we learned about the concepts of prevalence and incidence and how they relate to one another. Remember, the more incidence there is, the more prevalence will go up. Prevalence will be lower if people are dying more often or recovering more often. So there is this direct relationship between incidence and prevalence. Incidence being the onset of disease, we're watching people get sick. How many people are getting sick versus the prevalence. What is the burden of the disease in our population currently or at a certain point in time? Now, I showed you this last week. This hopefully should be a quick lecture because this is it. This is really all you need. We're going to talk about, every piece of this and why this matters. But if you had to rip up the rest of your slides and could only take one slide from this lecture that I haven't even started yet, it would be this slide from last week, okay? These are the equations that you need to do everything. Not hard equations, right? The math itself is not hard. I promised you that. I promised you, hey, it's PEMDAS at worst. But what is difficult is plugging the right thing in, subtracting the right things out, understanding what each of these numerators and denominators actually functionally is, and where to get those numbers from what I give you. Now, I'm going to just talk about this now with multiplier. You will get, since we're dealing with like population health, usually it's like crazy small numbers and crazy big numbers because hopefully not that many people in a big population are getting sick. So ideally, again, very small number, very big number. It's very difficult to interpret like 0.00008. So we can multiply. Either to make it a percent, you multiply just by 100, right, to express whatever this would be as a percent. Or you can multiply it by 1,000 and then whatever unit it was would be like 1,000. So like, for example, an incidence rate, the units would be person time. So like cases per person years at risk. And then instead of having it be per 1 person year, if you multiply by 1,000, you would get a bigger number. And that would make sense for 1,000 person years at risk. So, I guess my suggestion is do all the math first, and at the end you can do a multiplier to make it make sense. But don't just try and work in percentages the whole time. Okay, I haven't even told you anything yet, so let's go. Today we're talking about measures of disease frequency. Remember, we're just talking about outcomes at this point. Next week we'll talk about exposures and outcomes and association. This time we're just talking about frequency. How frequently do we see a disease in our population? And how do we express that? We use measures of disease frequency to describe the amount of disease, disability, or behavior within a defined population. We can use frequencies to compare frequencies. Or is one population sicker than another? And related factors between or within populations. We can use measures of disease frequency to predict the probability that an average individual will develop disease. And we use it as a measure to provide information to measure associations and excess risks, which does mean that next week, this is what we're doing, and we'll need these numbers for that. So what do we need to know to calculate measures of disease frequency? We talked about these things last week. So if that really left your brain, go listen to last week's lecture on 2 times speed. Just let it wash over you to remember these. You need the measure or definition of disease. We talked about case definition last week. You need to know concretely, as concretely as possible, what your disease definition, your case definition is, so that you can track people accurately if they have the disease or if they don't, so that there's no gray area. You would need the number of people affected. Again, we're tracking disease, we're measuring it. If we haven't measured it, we don't know. We have to know the size of the population at risk. Let's go back for a second. This is total population, that's fine. At risk, and at risk at the start of the observation period. So what do we mean by at risk? We have to know, this is the denominator. What is the denominator? And that tells us about who is included in the data that lets us understand risk. Now, last week I showed you a slide with a little kid, and he had chickenpox. And he was not at risk for chickenpox because once you have it and you recover, you are immune. He can't get chickenpox again. We also talked about, for example, if we were talking about risk for ovarian cancer. Who is not at risk for ovarian cancer? Okay, males, no ovaries. People who have had an oophorectomy, which is you have your ovaries removed, not at risk for ovarian cancer. Third population that's not at risk for ovarian cancer is people who currently have it. If you currently have the disease, you're not at risk for the disease. If you have COVID, you're not at risk for COVID. If you have a concussion, you're not at risk for a concussion. Well, in a way, you're at risk for a worse concussion, but like a easy degree concussion, you're not at risk for the thing that you already have. So, you need to remember that when we're thinking about our denominator. You need to know if your population is fixed or dynamic. And we talked about the difference last week. Remember, fixed is you're a member of that population forever. The only way to leave it is to die. No one is entering that population. Dynamic is it can change. The amount of people in San Diego is probably changing right now as someone's crossing county lines or city lines. Either one. You need to know if it's the new or existing disease, event, or state. And you need to know the time period of observation. 5 new cases of a cold in a day is very different than 5 new cases of a cold in a year, right? So we need that for interpretation to understand really how frequent it is. We need that time. This is a practice problem for later. I actually don't love how this is depicted, and you will have to calculate incidence rate just like this on your homework. They ask for per 1,000 person years, so again, that's what that multiplier is. I guess what I want to point out to you here, I actually don't. I think we might come back and talk about this later, but not certainly. This will be a practice problem for later. We'll do it in an activity, possibly. Okay. The goals of a measure of frequency is to measure the distribution of the disease, to assess burden, and to compare between groups to identify disease determinants. Again, we're not even measuring the association between the determinants of the disease, we're just comparing between groups to identify possible determinants. The key components of a measure of frequency always is the number of individuals affected by a disease or health state. Baked into this is a solid case definition. Excuse me. The size of the source population, out of how many people are we talking about, and time. Even if it's not part of the equation, you need to know, again, 5 cases of a cold in a day, very different than a year, so you need to know time. Counts are the most basic measure of disease frequency. Again, you need a clear case definition, and these definitions can be based on signs and symptoms. 18 of my students experienced fatigue, chest pain, and a wet cough. And that's our case definition for one thing or another. 18 of my students, or 20 of my students, I should change the number, experienced headache and nausea. Disease definitions can be based on clinical exam. I'm trying to think of one. Like if they want to assess viral suppression, they can take your urine, see if you've been taking ART. They can test things in your blood, clinical exams. Laboratory test results, the biopsy came back positive, etc. If you've had a formal diagnosis, if you experience signs or symptoms of depression, any of these can be disease definitions, just depending on, but it'll be operationalized differently, probably in every scientific paper you read. Yeah, and you'll see this variability in definitions by the investigator, geography, secular trends, so take notice. In mental health research, I can ask, there are ways for me to give a questionnaire and see if someone's depression symptomology meets a threshold for what we care about. Or we can just ask them, have you ever been told by a provider that you have depression? There is a way that captures a very different population, right? Even though both were thinking about depression, the ways that you want to consider it and measure it can have implications for your findings. And so you have to justify whichever one you're going to do. Okay, first thing you need is count data. You just need to know how many people are sick. So let's say, for example, in California, we have 1,811 new diagnoses of HIV. In Louisiana, we have 842. This is important for public health planners who make decisions about resource allocation, and it's a good first step. However, do we really, with this alone, want to say, oh, California has more burden of HIV than Louisiana? You might be thinking in your little brain, California's a much bigger state than Louisiana. And you'd be right. The second thing you need is the size of your source population. Populations are groups of people with a common characteristic that gave rise to the cases, in our example, either living in California or living in Louisiana, being place of residence. But they can be defined by many characteristics. It can be people of your age group. For me, it would be 25 to 34. It can be people of your same sex, male, female, or intersex. Those are the three sex options. Of your race or ethnicity. It could be occupations. We're comparing coal miners to ballet dancers in terms of lung health, something like that. Place of residence, like we said, or a life event. If you have received a tetanus shot in the last 5 years, if you've given birth, for example. Motor vehicle accident survivors, amputees. Those can be populations. You've seen this before. It can be fixed or dynamic. We've already talked about that. Boop. There you go. Your count data is much more informative now that we know the size of the source population. And here we've defined it geographically. In California, we have 38 million residents. I don't know how current this is. I guess we'll find out. In Louisiana, you have 4.6 million residents. I don't know how current this is. You want to know, because the last thing you need for a measure of disease frequency is time, okay? Length of time is this how long the source population was followed. This could be a single point in time. We got them all at the census. No, not everyone is taking the census exactly at the same moment in time, but that still counts as a single point in time of like, that was one measurement of everyone. Same or different calendar time or varying lengths of time. We'll talk about this varying lengths of time. I kind of spoiled it with the practice problem. How you'd want to track that if your source population was followed for varying lengths of time. Boop. See, in California, this is the first half of 2011, whereas Louisiana, this is all of 2011. So not only was this not telling us a lot in terms of the source population, but this is only over 6 months, whereas this is over 12. Now, these counts are even more informative and fair comparisons can be made. So, what's our annual rate of HIV diagnoses? In California, it's this 1,811 over 38 million over half of a year, which comes out to 9.5 cases per 100,000 person years. Again, it was a very small number, so we added that multiplier to make it more meaningful, per 100,000 person years. And the annual rate of HIV diagnoses in Louisiana is 842 over 4.6 million, and we divide by 1 year to get 18.3 cases per 100,000 person years. If we had just had these two numbers, you'd say, oh yeah, HIV incidence, new diagnoses of HIV, higher in California. In fact, not the case. And that's a fair comparison. You'd need all three of those components. Now, incidence measures, we talked about this last week, measures occurrence of a new disease that develops in a population at risk over a specific time interval. Those are the three components of risk. See all those things that we need. Source populations is considered to be that at risk. So again, in this, our source population was just entire residents of the state, but now we're considering it to be people at risk. That's part of the denominator. So we'd want to count the people that are disease-free at the beginning of a study. If, on your homework, I give you a question that is like, oh, we sent out surveys to 100,000 people or something, and we followed them over time, and a certain amount of them developed disease, but a certain amount of them had the disease at baseline. You'd want to subtract those people out from the denominator because they're not in your source population because they weren't at risk when your study started. Does that make sense? For people to transition from health to disease, there must be an element of time. We want to use risk. If we're talking about risk, most likely and mathematically, we're talking about incidence. We want to see people get disease. Well, we don't want to see people get disease, but to understand risk, we have to observe people getting sick to be able to say anything concrete about risk. Now, there are two main types of incidence, and that's cumulative incidence and incidence rate. We defined these last week. Let's learn how to calculate them. Cumulative incidence you're going to like a lot more, but we realistically can't calculate this a lot. Cumulative incidence estimates the probability or the risk that a person will develop disease during its specified time period. It's just the number of new cases of disease during a time period over the number in the at-risk population at the beginning of that time period. Oh, there were 1,000 people at risk, or there were 100 people at risk at the beginning of 2024, and 4 of them got sick. Incidence rate, cumulative incidence rate is 4%. Easy, simple, easy, simple. However, this assumes that the entire population was followed for the entire specific time interval. Basically, a closed population is that during your time interval, no one entered and no one left. That's hard to achieve. So no limited losses to follow-up. Your follow-up has to be really, really good for you to be able to calculate a cumulative incidence. Now, I think that for something like my students over a semester, I would consider you a closed population. I can contact each of you readily. But there are very few situations where that happens in the health world. Usually getting people at their job, at a job site, is a pretty good way of keeping a closed population. If they have low turnover, you can get an employee bank of people and follow them and to understand incidents. Like a sports team as well would count as a job site. You've got people committed to something for like an entire season. So you should be able to follow up that population for the entirety of your time period. Beyond that, it's difficult. Nursing homes are pretty good for cumulative incidents because they live there and they're under constant watch. Prisons are good for cumulative incidents for the same reason, unfortunately. What others? I'd say just know this assumption. If it is a population that is transient and like preschool enrollment, new parents are coming in and dropping out. Oh, Milo, your TA hopped down. All the time, you can't calculate cumulative incidence, and we'll talk about what you would do in that situation. Cumulative incidence is expressed as a proportion where the numerator is a subset of the denominator. So it'll be a range 0% to 100%, or 0 to 100 if you don't want to calculate it into percent. Again, if I have 100 students and 4 get sick, cumulative incidence over that time period is 0.04. Or it could be 4%. For example, let's take the example of diarrhea during a 10-day follow-up period in breastfed infants colonized with cholera by the level of antibody titer in the mother's breast milk. So among the total population, 19 babies had diarrhea out of 30. So the 10-day cumulative incidence, and again, 10 days is not that long, so realistically you could imagine a closed population here. It's going to be 0.63, or 63.3%. Now, we'll look at this next week and look at these exposures, but let's just calculate the cumulative incidence among those maternal antibodies. Those with low maternal antibodies, it was 12 out of 14. The 10-day cumulative incidence among this population was 0.857, or 85.7%. Whereas among mothers with high antibodies, it was 7 out of 16, 43.8%. These estimates can be interpreted as risks because we're watching babies get diarrhea, and the population is fairly stable, again, because it's 10 days. Now, I gave you a little warm-up last week to think about. A rate has time in the equation. And I gave you this list of different calculations, like infant mortality rate. I gave you proportionate mortality. I gave you crude mortality. Many of these are not true rates because the time is not... You have to specify time, remember, as part of the disease frequency, but it's not in the equation. So case fatality rate is a cumulative incidence measure. You're looking at the incidence of death among a source population. But it isn't a rate. So it should be constructed for a specified time interval. Again, number of deaths over cases in a day could look different than over a year, depending on the disease duration. And that would reflect the severity of disease. So let's imagine a population of 100,000 people and 20 are sick with the disease. Within the first year, 18 of those 20 die of the disease. This was actually a total tricky little thing that I gave you. The case fatality rate is 18 over 20, or 90%. Most people who get this disease will die from it. 90% of them, in fact. So that's case fatality rate. Sorry, my cats are being strange on the ground. Oop, skipped one. This is important. Incidence rate. Acute time with just one fraction is over. Incidence rate is the occurrence of new cases of disease that arise during person time of observation. Now, I told you, having a closed population is that prerequisite, is that assumption, that requirement for calculating cumulative incidence. If you don't have that, and you have an open population where different people are coming in and accruing or are there, and you can track them, but only for different amounts of time, like you can only you have awesome participants who you can get in touch with for 12 years, but others you only hear from for 3 years and then you lose track of them. You can use person time as your denominator and calculate incidence rate. So, with incidence rate, it's the number of new cases of disease during that specified time period over the total at-risk person time of observation. It's a new concept, but it's not just the source population, it's how much time they give at risk to that denominator that you are following them. So time is in the denominator and therefore the units, and because of that, it's a true rate. Like cumulative incidence, this only includes new cases. You'd want to take, again, same thing with the principal at risk. if someone, doesn't matter if you're following them for 12 years, if they were sick at the beginning and they stay sick the whole time you track them, they're not at risk of getting the disease. Unlike cumulative incidence, this does not assume that everybody was followed for the same amount of time. Individuals can contribute different amounts of person time to the denominator. This is useful for dynamic populations or high losses to follow-up. And only person time under observation contributes to the estimate of incidence rate. If for some reason, I don't think I included an example like this in your problem, I was able to contact you for 2 years to understand your disease status. Maybe I'm looking at incidence of concussion, and you're supposed to call me every time you get a concussion, and I email you every year like, hey, did you get a concussion this year? And I am in contact with you for 2 years. You've given me 2 years of person time. Then I lose touch with you for 5 years. I'm still doing my concussion study, but I lose touch with you. Then my research assistants get a hold of you again. I could add more person time after, but not during if you weren't under observation. This is also called incidence density. I will literally never use that term in this class ever again, but just know it. You might see it in British journals. So let's talk about the accrual of person time. We could spend an entire activity drawing these. Let's imagine that a dynamic population of 5 individuals is followed for a 5-year period. These are all 6-month chunks where they were contacted in January and July of a year. So this first person, at the very beginning, we got 2 people. This person was followed up for 2 years, and looks like we lost them to follow-up, and as far as we know, they didn't get whatever disease we're talking about. The second person, we enrolled them a little later, so we don't know here, we weren't tracking them here, but we followed them for 1, 2, 3 years until they did get sick. They did get sick. And so how long were they at risk? Yes, there'll be a case in our numerator. How long were they at risk? 3 years. So they contributed 3 years of person time, at-risk person time, to our denominator. This person is our golden child. We followed them the entire period, the entire 5 years, and they did not get sick. So they, thank you, are not a case and added 5 years to our denominator of person time at risk. Subject 4, we got them a year in, let's say. This dot should really be here. Let's just assume that we got them for the perfect 4 years. And we were able to follow them for the last 4 years, and they did not get sick. They're not a case. And our 5th individual, we got them 2 years in. 2.5 years. Oh, I see what happened. We got them 2 years in, and then we had them for 1, 2.5. And in this last half, they're no longer at risk because they are a case. So here they're contributing to the denominator, and now they're a case, they're in the numerator. They contributed 2.5 years of person time to our denominator. So what will be our numerator? Going back, what's the number of new cases during this time period? It's 1, 2. And what's our total at-risk person time of observation across all 5 people? 2 plus 3 plus 5 plus 9 plus 2.5 is 16.5. So 2 new cases over 16.5 person years is 0.121 cases per person year. Again, this isn't really meaningful to us. We don't know what a fraction of a case means. But we can multiply by 100 and express 12.1 cases per 100 person years. Over 100 person years, we'd anticipate 12 cases, roughly. You will have a problem just like this on your homework. In fact, it's not just 5 subjects. I think it's 8. And it's not just 5 years. I think it's 12. So this is the type of stuff we'll spend an entire day doing. Doing in activity. And this is the tool to help you count this person time. To do this the math itself is very simple. but you want to make sure you're counting person time correctly. And I know it's a new concept to you, so please reach out if you need help. Also, I just will say, assume as well that this in real life people get sick all throughout the year. Here, we're assuming that just when they're getting sick right on what January 1st of 1999 or whatever. January 1st or July 1st of 2000 or whatever. And that we first contacted them on January 1st. In real life, this isn't the case, but I want for you to have easier numbers to work with. You can assume that it happens right on that line of per year. Okay. If, this was only 5 people, and you can draw it, but perhaps I just give you the person years instead of giving you information about each subject. You can do the same thing. Here, we're looking at breast cancer cases and person years of observation for women with tuberculosis who were exposed or unexposed to multiple X-ray fluoroscopies. Oh, I need a slug of coffee after saying that. Okay. So, among the total population, 56 people got breast cancer, women in this case. 56 women got breast cancer. Over, in our source population, we have 47,027 accrued person years at risk. 56 divided by 47,027 is 11.91 per 10,000 person years. It's probably a disgusting fraction, and then you multiply by 10,000 to get a number that we like and can interpret more easily. Among women with X-ray radiation exposed, it's 41 cases. There were 41 cases over 28,010 person years at risk for an incidence rate of 14.64 cases per 10,000 person years. And for those with no X-ray exposure, it was 15 over 19,017 person years for an incidence rate of 7.89 cases per 10,000 person years at risk. We'll do more with these next week. I do want you to know the relationship between cumulative incidence and incidence rate. For when cumulative incidence is small, it roughly equals incidence rate times the time period. I could give you proof of that. Really, I should. I think just take it for what it is for now. If you go onto your master's and get a master's in epi, they'll ask you questions about this, but I won't. Assuming that most of the population was followed most of the time, it'll equate more directly if you have more of the population followed for more of the time. And for diseases where incidence is high, where cumulative incidence is high, greater than 10%, this is not true. Oh, I do give it to you. Look at me. So let's imagine influenza in the workplace. 600 people are followed during a 6-month period. Total person months of follow-up is 3,200, and we observed 16 cases of the flu. This cumulative incidence for 6 months in a workplace we can follow people is 16 over 600, so that's about 2.67. The incidence rate, again, if we follow 600 people for roughly 6 months, should be like perfectly it would be 3,600 person months, no? But roughly, we did pretty good. We followed and got 3,200 person months at risk. Also, people were getting sick, so after they get sick, they aren't accruing person time at risk, right? 16 over 3,200 person months is 0.005 per person month, or half a case per 100 person months. If you multiply our incidence rate, which is this, multiplied by our 6 months, the months cancel, and then you get 0.03, which is about 2.67. So you can approximate. This approximation works because of the low risk. It's not true if you have a more incident disease. And note that most people have to be followed for most of the time. Workplace studies and 6-month follow-up periods, feasibly we could do that. Some final notes about cumulative incidence and incidence rate. You probably already like cumulative incidence a lot more because it's easy to calculate and understand. But it does require certain assumptions for accuracy. So if your data aren't configured that way, you can't calculate it. Whereas incidence rate is harder to calculate and less intuitive. Person time is a concept that some people just really do not take to, but its accuracy does not depend on the same assumptions. And it most often reflects the real world in which we try to work with dynamic populations. And then prevalence. It's just one equation. We're gonna come in under an hour today, so I'm sorry about last week. Prevalence measures the existence of current disease in a population. It's the number of existing cases of disease at a specified time over the number of people in the population at that time. It's a proportion. It's not a rate. The numerator is a subset of a denominator, right? Either I'm a person and I'm sick, or I'm a person and I'm not sick, with whatever disease state. This can be expressed as a percent, and it's an estimate of the probability that an individual in the population has a disease. If I knew that, like, out of all my students, 10%, the prevalence of anxiety was 10%, I could look at you and be like, oh, 10% of you have anxiety. And each one of you would have a 10% chance of having anxiety, even though that's not how it's actually expressed. It's like just one of you out of 10 of you would be it, but that would be your probability that it would be you. Yeah, this is the answer to what is the proportion of population affected by disease at that specified time. It tells us about the burden. Remember the two types of prevalence. Do I talk about it? No, I don't. The two types of prevalence are point prevalence and period prevalence. Go back to last week for that. I'll only make you calculate it in the context of point prevalence. Or I'll just tell you the time period. It'll be point prevalence. Now, going back to the bathtub, incidence and prevalence tell us different things for different uses. You're like, Marina, why do we need all three of these equations? It's because prevalence can be useful for administrative public health activities to express burden of disease. And it's often easier to obtain this information. You could track it very easily. And that can project medical care need. Oh, this many people have type 2 diabetes. We need to start making some insulin. Type thing, right? Whereas incidence might be useful for causal inference, to understand risk. It is more useful in etiologic research. Etiology is we're looking at the causes of things, and we'll talk more about that. And we can also evaluate prevention efforts. If we really educate people about diet, does the incidence of obesity, does the incidence of metabolic risk go down? That's a way that we could use incidence to evaluate prevention efforts, right? Again, we're observing that transition from health to disease, and yeah. Incidence is often more difficult to obtain. I'll leave you on that. Now, this is stuff that really I'll leave for you to take in your master's if you choose to do so, is the relationship between point prevalence and incidence. When prevalence is relatively low, prevalence approximates the incidence times the disease duration. Disease duration being the duration the disease lasts in your body on average. Like cold is like a 3-dayer. Norovirus is like a 1 or 2-dayer, 48-hour disease duration. Diabetes, long duration. And this is only true when prevalence is relatively low. And this assumes that incidence and duration are constant over time, so that it happens at a steady state. And if incidence is low but duration is long, point prevalence is high relative to the incidence. This should make sense. Like, if you are dripping slowly, the drips are slow, but people are in this bathtub for a long time, then there are going to be more people in the bathtub than are dripping. If incidence is high but duration is short, then point prevalence is low relative to incidence. Here, imagine our faucet's really drippy, but people are leaving the tub. Either it's leaking or they're all steaming out. So the tub is like near empty, but there's a constant drip. Oh, I'm so sorry if you can hear the garbage truck that's outside my window right now. And change in prevalence can be due to changes in duration, incidence, or both. Either you can turn up the faucet and suddenly the prevalence goes way up, like with COVID, or people can be living with it for longer. Sad but true, but like HIV. HIV is not the death sentence it once was. Now we see people living with it for a longer duration in time, so it's more prevalent. Okay, that's it. In summary, no definitions and formulas for cumulative incidence rate, prevalence, and how the measures are related. For all measures of association, know how the counts, populations, and time are included, and use correct units. And I'd like you to be able to put estimates into a sentence like I've been doing. Yeah, well, this should prepare you for Unit 2 homework. Your job is to take Quiz 6, and look at Unit 2 homework, I'd like you to look at it. Even those of you who are coming on Thursday, I'd like you to look at it. And then we'll do questions 1, 2, and 3 together on Thursday, so you don't have to do it. But if you're not coming to activity, you do have to do it. And that's that on that. I'm happy to... You know how with Unit 1 homeworks, I was happy to look at drafts just via email. With Unit 2 homeworks, I'd really like to focus my energy during activity or during office hours. I prefer you not to just send me this and be like, hey, is this correct? Schedule time with me in office hours or come to activity. If you're like, hey, Marina, I'm not free during activity time and I'm also not free during your office hours time, schedule that with me. That's when I'd like to discuss your activities because they are graded for correctness, so it will matter. Not to say that I'm not available to you, I super am. Just those will be the times reserved for that. Okay. I literally just said that. You should be able to do problems 1, 2, and 3 on your homework after this lecture. 4, 5, 6, 7 should look confusing as shit to you. Don't worry about them yet. Yeah, I just said that. Quiz 6 is due Thursday, and those of you who I won't see on Thursday, enjoy your spring break. Enjoy your spring break. Okay, let's do the puzzles. There's a new one. I'll stick around for questions even though no one's chatted. We're gonna do more puzzles because today was a short lecture. If you don't care about the puzzles, you can click out. Let's do them. For today's Wordle Day, let's do risky. We've been talking about risks. Let's do risky. It's kind of a horrible start word, but let's get at it. That was a garbage start word. Let's go. Death. Ooh, okay, let's go. Oh, I was gonna do healed, but then there's no D. Is there a world where it's something like this? I don't think so. What could that feasibly be? Hello. I might tank it and just guess a letter that I've already guessed and guess heavy. Oh, it's heave. Of course. I should have thought about that for one more second. Okay, that's the Wordle. Connections. I blew it last week. I was really embarrassed and I was tired after 2 hours of lecturing. Oh. How interesting. Okay, plus division. That's what they want us to think. Oh, and with. This is one. Like in addition to. There we go. Including. Okay, rank, class, division, tier. I don't see that going badly. Yep, section. Okay. Golden, lab, Boston, and pit. These are the first words in dog breeds. I don't know what this is. It is famous poems. Oh! How interesting. Well, that was my redemption arc. Have you seen this new one? Strands. You have to fill up theme words to fill the board. So let's do them together. And then this yellow one is your theme word. Or is the theme, rather. The spanogram. And then we can find things to get hints. Okay, ruler's decree. Sure. Will just get us closer to a hint. Boop, boop, boop. Oh, I thought we had lament. Lament. Lamer. Tamer. Tame. We could get a hint. Let's get a hint. Yard. Okay, it's measures for sure. So let's find some more. I'm looking for like mile. I'm looking for feet. Maybe oh, foot. I'm looking for the word length. Long? Had to. Inch. Meter. Nope. Meter. Sorry. Meter. Oh, what is this? Mints. Measurements. Measurements. That's the spanogram. What is this? Fathom. How long is a fathom? Oh, is this league? A league? And a furlong? No way. We did it. And I'll be putting the results in the YouTube chat. Paste. And last one, we're going to start doing the crossword mini. Because I'm beast and baller at it. At least I hope I will be it today. Fair use. Sense. Misbehave. Act up. Act up. A little suspicious. Suspect. Ball. Poor passer. Let's try. No longer on social media. Hot guy. Stud. Was I right with act up? Sports word. SB. Cash. I was right with act up. That's crazy. Something a bat listens for while flying is echo. Shady and ball hog. Okay. 7 seconds. My record is 8. And we got no questions during that time. All right, you all take care, and I'll see you on Thursday. Bye-bye.